Jai Hind. Today we are going to discuss few local search techniques. Till now we have talked about informed search and uninformed search, different ways of searching under both the categories. In one we will have some uh, given information, and in few we are having just the problem definition. And whatever we have talked about till now with informed and uninformed search, in that we were talking about the path to achieve the goal. Now we'll talk about a different type of techniques required under local search techniques. In this we will talk about what is local search, and we'll talk about three different algorithms: hill climbing, simulated annealing, local beam search, and genetic algorithm. So the first question is, when we are having informed search and uninformed search, and we are talking about the state transition based on the information whatever we are having, then where do we need this type of search techniques? So we'll talk about that category of optimization techniques now, optimization problems now, in which we will not talk about the path. Okay, so we have that category of problems we'll talk about. In many optimization problems, the path to the goal is irrelevant. For example, if I am playing chess, okay, then what is there? I'll take few moves, then another move. My opponent will also take some move, one move after other. Both the players will go on taking the moves. Now the question arises that the path means the sequence in which the moves have been taken are important or not when we have won the match. It is irrelevant which step I took, that doesn't matter after I have won the game. Okay, so we are having this type of problem in which the path to the goal is irrelevant, but what is important, that is the goal state. The goal state is the solution. For example, if we have the chicken mate condition, how did we reach there? That is not important. The important is the chicken mate condition, that we have won the game. Okay, so in this type of problem we apply local search techniques, local search algorithm. Local search algorithm means we will not talk about the path as we talked in informed and uninformed search techniques, but we will talk about the solutions. Okay, so what we are having here in local search algorithm to be noted, we will have some state space. What that state space will be? It is set of complete configurations. We will have the state configurations. This is our state configuration. Now what this will be, what we have to find out, because we are given some initial state condition configuration, what actually we have to find? We have to find some configuration which will satisfy the constraint. For example, chicken mate, that is having the constraint. That constraint is the condition that is having some conditions. That is what we call here constraint. That is check and mate. If I take another example, now my example is of n queens problem. In this n queens problem, what I am having, the 4x4 board I have taken here. So we need to put 4 queens. Now what is my board in n queens problem? That is n by n, as we have on the other slide. What we were having there, n by n board, so 4x4 board was there. What are the constraints? Constraints are that queens must not be in same row, same column, or same diagonal. So that is the condition. So what is the solution? Solution is that state, that goal state in which there is no queen attacking in same row. It means there is no attacking pair in row. Row means we are not having 2 queens in the row. Okay, same in column. and diagonal. So this type of cases where we have this type of situations, we use local search technique. So what is to be noted here? What we do in local search techniques? In local search techniques, we keep a single current state and will try to improve that. Okay, it is not like that the informed search or uninformed search, that we are having multiple branches and we are searching through that to which side we should move. No, we will have just the current state and we will try to improve it. So in local search algorithm, from here we came to know about the 2 points, that we take the current state and then we try to improve that, and second is we are not talking about the path. Path is not important. We are talking about finding the constraint satisfied, that is our goal state. This is the example we have taken here, 4x4 board. Okay, if I say in this queen is making attacking pair with this queen because these are in same diagonal. This is making with this because these are in same row, and this is attacking with the same diagonal. Okay, so what we can do, this is our current state. To this current state I can make an improvement. What is that? Let me try to remove this clash. What this constraint dissatisfaction, what this clash is, these are present in same column. So I moved this here. So what has been done? A queen has been moved in the next row because it was having clash with the same row and same diagonal. So we changed it to, we shifted that. So we can see now we are in a better position. Here all the queens were attacking each other, but here if I say this one, it is not attacking with others. So what one is attacking now? That is this. If I shift this to this, I just shifted this queen here and this queen in this particular case. So we made changes in current state and we have got improved next time. Okay, now if I consider this, in this only one pair is attacking. And what was there? All the pairs were attacking. Okay, attacking means either they were in same row, same column or same diagonal. So what happened? After moving these queens to different rows, okay, we are improving the condition. This is local search algorithm. The current state has been improved in this one and this further has been improved in this one. So we'll go on improving. If we see this one, in this one is not attacking now, this one is non-attacking, only one pair is left. And what was there? All the pairs were attacking. Okay, so we got this better situation now, right? Now we'll talk about the different algorithms. So first one is hill climbing search. In hill climbing search, what we do, we just see that this is the one state, current state, we have to improve it. Okay, now we have to improve, so we need to move to some better state. The current state is to be improved. Okay, so what hill climbing says? Hill climbing says that it is like climbing Everest. It means we have to improve. Climbing Everest means we have to go upside. Now what to go upside? Objective function. Our objective is to implement all the constraint. Okay, so we have to do the better one. So our solution should be better. So it is just like climbing Everest. And what is the second condition with hill climbing search? It talks about the thick fog. It means we are just able to see the next state, not next to next. Because of thick fog, everything is hidden. I am just able to see my neighbor state. Okay, what will be the next state? So in a particular state, I can see the current state and all the neighbor state only. I am not able to see the neighbors of neighbor state because of thick fog. Okay, so it talks about that situation should get improved and we should just see the neighbors. Okay, and the last one is amnesia. Amnesia means we will forget what we have already done. Our memory is very short. We cannot remember what we have done before coming to this condition. That is amnesia. Okay, so if we have just improved the situation, again we will consider that neighbor also from where we have moved to this particular state. That is hill climbing search. Okay, now let us talk about this hill climbing search. If we see this, this is one state and we have moved queens and then we are getting this state. Okay, so we will take the current state. Okay, and what are the current next state possible? Either I move this queen, or I move this queen, or I move this queen, or I move this queen. That are the possible state. So one of the states is that I moved this one. So these are the possible positions that so many queens are attacking. So I can change only position of only one queen. That will be the next state. Okay, so based on this we will check that we are taking as input the problem, the current state and the neighbors. The current state is queens are in that position. What are the neighbor state? Just moving one queen. Okay, so different queens will have the different state space situation. So what we will do, we will go on doing this. What we will see all the neighbors. 4 queens were there, so 4 queens we will move and then we will see all the neighbors and their evaluation function value. Now which one will be selected? Among I can move first queen, second queen, third queen, fourth queen, but which I will select? I will select highest valued successor of the current state. Whatever is my current state, I will take the highest value successor of that. If the selected highest value is less than the current state, it means current state is better. Okay, the next state will not improve our situation. So we will keep the current state only. It will return the current state. Otherwise, what it will do, if it has gotten a better value for neighbor, if it has a better value for neighbor, then we will search more. Neighbor will be taken as the current state. The current state will get changed. If neighbor value is the highest, best neighbor among the current state neighbors. Okay, if those are not better than the current state, then current state is actually the maxima. This is the maximum evaluation that we are getting. If we have got a better neighbor, okay, a better neighbor state we have got, in that case we will take that neighbor as the current state and we will try to find a better situation, more better if it is possible. So we will go on doing this, we will go on taking the neighbors and we will go on moving to the neighbor until we get a maximum value. It means we are not able to improve much. So let us understand it with the state space. This is my state space. If I see this, this is my states, set of states, and this is the objective function. Okay, so all the possible situation, maximum possible situations are shown on this particular slide. So if I see, this is a situation where we have reached to a maximum value. Okay, now the question is, what type of maximum value? Maximum value in its surroundings. If I see, this is another maximum, maximum in its surroundings. And if I see this one, this is also maximum, and we can see that in whole search state space, it is the best one. No one is better than this. If I see this one, this maximum value is better, but no one is better than this. So this type of situations are called local maxima. What are local maxima? Which are better in surroundings but not the global one. We are having a much better solution present here. And which is the best among all, that is called global maxima. So we should be able to reach to the best solution, that is having the global maximum value of the objective function. This type of situation is also called flat area. Flat means plateau. Plateau means we have reached to a situation where neighbors are also of the same objective values. Objective function value is same for all the neighbors also. Okay. So, if I see this one, in this there is a local maxima which is having flat. This is another local maxima which is not flat, but it is having the better value in surrounding. If I see this one, this is a flat area. Okay, but we are having better situation on one side of this. This is called shoulder. Shoulder means better than many values, but still there is possible better objective function value. So, this is the possible state space that we work with in all the local search techniques, and here we are talking about the hill climbing search, that what hill climbing search can do and what not. So, let us talk about what it is not able to do, that is part of problems with hill climbing search that should be addressed, and later we will see that there are methods that address this particular set of problems. So, first one is local maxima. What is the problem of hill climbing search? If we see this one, if there will be some initial state, let me say my initial state is this, so that will be my current state. Okay. So, if I am taking this as the initial state and I will see the neighbors, these two are the neighbors. So, which will be selected, which is having better evaluation function? This one. So, we will go on improving it and finally we will reach here. Now, we will not get any better solution. So, we are not getting any better solution, but it is also a good solution among surrounding. This is local maxima. So, we got a solution, but that is good among the neighbors. That is not the best solution. That is better than the neighbors, but not the best solution. Why? Because we were searching in this particular area. If by chance we have selected this as the initial condition, this could be the case that after going on improving, we might have reached to the global maxima. So, what the question arises here, that it could be the case that we are not able to reach to the global maxima. Our problem is of local maxima. A local maxima is a peak that is higher than each of its neighboring state, but lower than the global maxima. The hill climbing algorithm reach the vicinity of a local maxima will drawn upward toward the peak, but it will be stick and nowhere else to go. It means it will reach to the local maxima and it will not be able to reach to the global one. That is the problem with hill climbing search, one of the major problems. Second is, if we are having a very small sequences of local maximas, those are called ridges. So, when we are having ridges, that is a sequence of local maxima. So, it is very difficult to come out of these, or very difficult to navigate, because we are applying here greedy algorithm. What greedy algorithm we are applying? We are just looking for the better neighbor solution, and we will go on searching and we will not get a solution here. That is ridges, problem with the hill climbing search. And the last one is plateau. Plateau, as we have seen here, these are plateaus 1 and 2. What are these situations? We are in this current state and both the neighbors are of same objective function. Both have same objective function. So, what we will select? A plateau is a flat area of the state space landscape. It can be a flat local maxima or it can be a shoulder, okay, from which progress is possible, but we are not progressing. We are able to see the shoulder problem. At one side of shoulder, a lower objective function means poor solutions are there, but at one side better solutions are there. These are the better solutions, but we are not able to navigate. That are the problems with hill climbing search. So in hill climbing search, we just checked the neighbors. Okay, so we are calling thick fog is there. We are trying to improve, so we are saying that we are climbing the hill, and as we are not looking beyond a level, so we are saying that we are not able to remember that, so it's amnesia. So this is hill climbing search. Now other methods we'll talk about which will address these problems. Simulated annealing. Simulated annealing is one more method, and what idea it takes. What is the idea for simulated annealing search? It says that what you are doing in hill climbing search, you are taking one current state. The current state is having the neighbor states. Okay, and what we are trying or what we are doing, we are trying to improve the current state evaluation. So what we are doing, we are finding the best neighbor in the vicinity. It may be some of the neighbors or it itself. Itself means reach to the local maximum. Okay, so always we are taking a neighbor state which is having the better evaluation function. If you see this one, I am here, okay, but if I do not take this value and I jump somewhere else, it may be the case that I reach to this situation. This situation means in the surrounding of global maxima. Okay, not talking about the better solution in the neighbor and going towards the local maxima. I take a jump from there. So I am giving some chances for jumping also. That is what the idea is. Escape local maxima by allowing some bad moves. So what we are talking about, take a random move. Okay. Now when we are taking random move, it may be poorer than that. It may be poor than the existing one. Okay. What we were doing in hill climbing, we were always taking a better neighbor, otherwise we were discarding the neighbors. So it allows to take bad moves so that the problem of local maxima can be solved. And it says that initially we have to try to reach to the vicinity of the global maxima. So take the bad moves initially and then decrease it gradually. So the frequency of jumping to bad moves could be allowed in the starting more than at the end too, because at end we need solution. We have to get the convergence towards the solution. So here we are having the concept of annealing. Let us firstly talk about what annealing is. Annealing is the process used to temper or harden metals and glass by heating them to a high temperature. So for material it is used. We will heat up the metal to a high temperature and then we will gradually cool it. How do we heat up and how do we cool it? That allows the properties, change in properties, thus allowing the material to cool into a low energy crystalline structure. So the quality of the glass or metal depends on, after heating it to a high temperature, how it has been cooled down. Based on that cooling process, the metal properties will be different. Okay, so that is the annealing process. So the same thing is talked about, that temperature here is the bad moves, maybe the bad moves, and when we decrease the temperature in annealing, that will say here that the later bad moves will be lesser. So let us talk about simulated annealing. So what we do, initially we don't talk about the best moves. When initial terms we take a current state, then we try to improve it, but it is not always improvement. It may be a random move. So what is the way of simulated annealing searching? It is not best but a random move if it improves the situation. When we took the random move, if the situation is improved, then it will be accepted. If situation is not improved, in hill climbing what was there, it was totally rejected, but here we will not reject it. Why? Because we are talking about this allowing of bad moves. So what we will do, we will accept it, we may accept it. So there is a probability of acceptance. It's not always 1, it is something less than 1. Always 1 means we are considering the bad moves. No, we are considering the bad moves with a probability. There are chances of selecting the bad move. Now when we are saying the probability decreases exponentially with the badness of the move. So probability depends on how bad the move is. We are saying that bad moves may be selected. Okay, so it depends on how bad the move is, means how it is worsening the current state. Okay, so the probability decreases exponentially. We said na, see this, we said that gradually decrease. So how this gradually decreasing? It is exponentially decreasing based on that badness. The probability decreases exponentially with the badness of the move. The amount delta E by which the evaluation is worsened, whatever will be the difference between the current and the bad move that we are taking as change in energy, that how much energy change we should have. As T goes down means with time, bad moves are allowed at start, then decreases. So what we will have? We will have the current node, next node and the schedule. How to take the downward steps. Okay, so we are having initial state. We will take the temperature schedule, how much to decrease. Okay, that is our schedule here, which has been defined. Now if this is 0, okay, initially, so we will return the current state. If T is 0, it means how it is depending? It is depending on the schedule. Now what we will do? We will take a random successor of current. Random successor of current. If the value difference of current and this next move, randomly we took the next move. If value of that next move is greater than value of the current, okay, so what does it mean? It means the next value is better, next state is better. If value of next state minus value of current state is delta E and delta is positive, what does it mean? Next state is better than the current state. So we will change the state as we said. If it improves, then select. Okay, so if next state is better than the current state, then we will take the next state. We will move to the next state. Otherwise what we said, we will not reject it. We may select it, but with a probability less than 1. So what that probability is? It means delta E is negative. Okay. So we will take the exponential probability. The next state may be considered, but with this probability of e to the power delta E by t. Okay. So what does it mean? With time, it will go on decreasing. The probability will go on decreasing with time. And how will be the, what will be the exponential component? That is delta. It will depend upon how bad the move is. So this way we apply simulated annealing search, and we are able to come out of the local maxima. So in hill climbing search, we have tried to simulate the process of annealing. So it is able to come out of the local maxima and may reach to the global maxima. Thank you. Jai Hind. In this video, we talked about the local search techniques of hill climbing search and simulated annealing. Thank you.